Debabrata will tell us about the first 10 to the power minus 32 seconds after the universe.
Today I'll be talking about the cosmic inflation, which possibly happened right after the Big Bang. In the opening slide, I'm showing you the logo of CMB Bharat Consortium along with the satellite image they have proposed to ISRO. We'll get to know about this in details at the end of my talk. Let me begin with the school day stories that we have been told that our universe is described by the standard Big Bang model. What this theory is about. So this theory tells that our universe began and at around 14 billion years ago, when the universe was like a hot soup of the particle and the radiation, and this starts to evolve and expanding according to the Friedman-Robertson-Walker metric, followed by the Einstein GR. And the quantum fluctuations right here just after the beginning of the universe have grown to form the present day structures of the stars and large scale structure around us due to gravitational instability. However, this model never tells you what causes this expansion. And it never also tells you where does this matter and radiation should come from. This model assumes that your space is somehow filled by this matter and radiation, and suddenly for some unknown reason we have access to it, and it starts expanding according to this space-time geometry. This Big Bang model is actually a bangless model. It's just an aftermath of the bang of the Big Bang. So to fill this gap, we need some prequel. During the early 80s, people have started to think what is the possible theory of that, and Professor Alan Guth come up with this idea, the inflation theory. So what this theory is about? This theory says that the inflation propose a repulsive gravity material. So this is counterintuitive than our notion of the Newtonian gravity. But believe me, under some circumstances, the Einstein GR can give you the repulsive gravity. So this repulsive gravity material stretches your universe so rapidly, exponentially, and within very short duration of time, this 10 to the power minus 35 second, it expands our universe at least 10 to the power minus 29. It can be more, but just to be consistent with the data, we at least need to have this 100 doublings of our universe. It should stretch at that, but by that amount. So, but this repulsive gravity material is very like unstable, and that's why this inflation phase doesn't stay very longer period of time, and quickly decays, and this decaying energy produces the primordial particle soup, and that's why this inflation ends, this prequel ends, and our standard Big Bang model starts. So as an observer, my concern is not to judge which model of the inflation is doing better or which is doing worse, because there is no single solution. There are at least hundreds of thousands models which can give you the exactly same solution. My concern is, if the inflation is the correct theory, I should see some signature in the cosmic microwave background polarization. What is it? So the very common thing of this inflation model is, so it can predict this gravitational wave. So it stretches and contracts the space and creates this tensor fluctuations, and when it passes through the hot plasma, so it creates this nice quadruple pattern around the scattering electron at the last scattering surface. The last scattering surface is the time when the CMB photon decouples from the matter, and it had happened around the 400,000 years later of the Big Bang, and in terms of redshift it is 1100. So when this gravitational wave passes, so this quadruple pattern creates around the scattering electron, and it generates this Cardley polarization pattern. We call this the primordial B mode polarization. So there is another types of the polarization which called the E mode polarization, but that is not the sourced by gravitational wave. So that is sourced by the scalar fluctuations generated during the inflation. We know the amplitude of this mode, but we do not know the amplitude of this mode, because we do not know at which energy scale this inflation had happened. So that's why we parameterize it in terms of the tensor to scalar ratio, which is related to the inflation energy. So So, if the inflation had happened, I should see this Cartley B mode polarization in the CMB. In the last 3 decades, we had a fantastic journey using these 3 space satellite missions from very coarse resolution to the very high resolution CMB map, and along with some ground-based CMB observations. And so, where we stand, this is the CMB temperature fluctuations power spectrum. So this power spectrum actually tells if your 2 points along the sky is like separated by this angle, how these CMB photons are correlated. So this data point matches with the lambda CDM predictions very well, and also we have some observations on the E mode polarization. However, we do not have any observation, or there is no predictions at which energy scale this inflation had happened. This is the primordial B mode power spectrum, but generated from the simulation, not from the data. So as of now, we have only the upper limit of the tensor to scalar ratio of 0.036, so this B mode power can have any tensor to scalar ratio below this. We do not know what this is exactly. So far, the CMB mission was dedicated mainly to the CMB temperature anisotropy measurement, but in the coming decades, we are going to observe the CMB polarization, and all of the CMB mission will be dedicated to the CMB polarization measurement. So here is some upcoming CMB mission from the ground. So this is the CMB stage 4 mission, which is under construction in the South Pole, and this is the Simons Observatory, which is also under construction in the Atacama Desert in Chile. Hopefully these 2 observatories will be functional at the end of this year. So we have also the space mission. So this is the Lightbird space mission selected by the Japanese space mission, the JAXA, and it will fly to the Earth Sun second Lagrangian point and will observe the CMB sky with very low resolution. So the major target is to detect only the inflation, but it doesn't have the very broad science goal. But we can achieve the broad science goal using some missions like the PICO, which is in the NASA's concept phase study. So this has not been proposed yet, but this will scan the CMB sky with very high resolutions and mainly on the polarization detections of the CMB. Now let me discuss what we Indians are doing in this worldwide effort. So this is the CMB Bharat Consortium. So they have proposed this ECO, the Exploring Cosmic History and Origin. The mission name is ECO, but popularly this is known as the CMB Bharat mission. So this mission was inspired by the European Space Agency's core mission, so when that was proposed at 2017, this mission's budget did not fit with ESA's M-class envelope. So that's why the ESA encouraged European Cosmology Consortium to consider a major international collaboration, and at 2018 the Indian Cosmology Consortium took this advantage and proposed this ECO mission with some modified version of this core proposals to the ISRO. So this is on 2018 this had happened, and this was like in the first phase selection process, but we do not have the fund sanctioned yet. So this mission will have this 20 frequency band starting from this very low gigahertz to the very terahertz range, and so you can see, so this dotted line at the noise curve for the Planck, for this Lightbird, and for this the ECO mission. So you can see these 20 frequency channels are designed in such a way that it can drop the noise by orders of magnitude. Compared to the Planck noise. However, the noise is not only the problem is something else. This is the CMB sky looks like when we tune the CMB satellite when we scan the sky in the CMB frequencies. So you can see, so there is a CMB photons, but this is highly obscured by some other emissions, and this is in the low frequency, that is barely you can see the CMB, but at high frequency you cannot see the CMB. So because at the microwave band, the CMB is not only the component. So we have the similar emission from our own galaxies as well. At the low frequencies, this is dominated by the synchrotron from our galaxy, and in the high frequency, this is dominated by the dust emission. So that's why you cannot see the clear CMB sky. So similarly, this is for the polarization. So these are the map from the Planck at these 7 frequency channels. So you can see this foreground emission drops like till 100 gigahertz, then again increase, because the foreground emission drops like till 100 gigahertz, and again it increase. So if you compare the relative amplitude, the relative B mode power across the frequencies for these three components, the dust, synchrotron, and the CMB. So this is the signal we are going to measure. So this is the tensor to scalar ratio for which the CMB signal we are going to measure. Since CMB is the constant across the frequency, that is why this is the horizontal line. And you can see that the signal is order of magnitude obscured by the dust and synchrotron. At the low frequency, the synchrotron dominates. At the high frequency, this dust dominates. Then my job is to develop the very efficient cleaning algorithm to disentangle this foreground emission from the CMB. How many minutes? Okay, so let's skip this slide, because I wanted to give you some flavor what we actually do. But we have very efficient foreground cleaning algorithm. So these are the 4 cleaning algorithm which Planck collaboration had used to disentangle the CMB from the foreground. So let's not get into details about the individual algorithm. Rather, I would show you some forecast study on the CMB Bharat instrument design. So here we have used the 2 very famous cleaning algorithm called Commander and the needlet internal linear combination method, and we have used the various foreground model and passed the frequency maps to these algorithms to clean the CMB from the foreground. Then we study how much the residual foreground can bias your tensor to scalar ratio estimation. So you can see the most of the foreground model can give you the null detection, because my input tensor to scalar ratio was 0. However, we could not clean this foreground, the synchrotron foreground, because we do not have the many frequency channel at the low end of the spectrum. That's why when the synchrotron model becomes complicated, we cannot clean this properly. So that's where I will end. So summary of my talk is, the primordial B mode is a promising probe of the cosmic inflation. However, the main problem is the foreground, which is at least 3 to 4 orders of magnitude higher than the signal we are going to target, and the B mode with very high sensitive space missions or the very high resolution ground based mission. I think we have the enough robust cleaning algorithm to disentangle the CMB, and hope we can detect the inflation in this decade. Thank you.